Hello all, welcome to my course on methods of adhesion measurement, theory and practice. We are at lecture 55 today and we are discussing about how we can enhance adhesion of an adhesive by employing mechanisms which are not viscoelastic, by employing physical mechanisms like crack arrest and crack initiation, by using contact area splitting, and then we discussed about virtually patterning the adhesive surface, and then finally we discussed also about the self adhesion hysteresis in the last lecture. So, today I will like to continue my discussion on self adhesion hysteresis somewhat more, and then I will discuss another very interesting mechanism which is known as the elastocapillary effect. The elastocapillary effect can also be used for this crack arrest on the surface of an adhesive. So, we will present all that. So, these are the references that I am presenting in every lecture, and also within these slides also I have given the references. So, if I have missed any of these references in this list, but you can see that in the actual slide. In the last lecture we discussed about the self adhesion hysteresis using this multi-layer microchannels which are embedded on this film, and we saw that in this indentation experiment this particular top surface, this 2 dash, this interface get bonds and then they opens during the unloading. So, in the loading and unloading data, okay, this shows hysteresis, and the hysteresis actually is quite lot, it is not small. So, we can employ this self adhesion hysteresis to enhance the adhesion that we have discussed in the last lecture. So, today we will like to show that the adhesive surface, this the inner wall surface of this microchannel, that also can be patterned. So, layer embedded with microchannels having topographically patterned surfaces. So, we can use the coupled effect of this contact area splitting, okay, and also this self adhesion hysteresis, both mechanisms. So, over here for example we have this microchannels which are embedded inside this adhesive film, has this channels embedded inside it, and then so you may ask for what are the kind of dimensions. So, let me give you some dimension of this films. So, let us say the film is about, let us say 1 to 2 millimeter thick, and then this channel dimensions will be about the thickness of these channels. So, the thickness of the channel may be about, let us say 100 to 200 micron, not more than that. It is one order of magnitude smaller than this film thickness, and so there can be 2 to 3 layers. So, let us say this is one layer of channel and then there is another layer of channel. So, between them again the gap may be about maybe 200 to 400 micron or like that. So, this dimensions can be optimized by detailed mechanical analysis, okay, of this geometry. It is difficult to do in analytical easy solutions. This needs to be done by using FEM or like that, which I am not going to show here, but I am just showing the physics of this mechanism. And as you can see, the parameters of interest here, the gap between these pillars which is there on the surface of these channels. Now, channel surface is decorated with this kind of pillars like this. So, we would like to take the advantage of self adhesion hysteresis. So, that means this surface will come in contact with this particular channel, the top surface of this pillars, but also this contact area splitting. So, contact area splitting and self adhesion hysteresis, both the effects can be together. So, that is the idea of this designing these adhesives and like that. So, here is a video of this experiment. So, here we bringing in contact this indenter, and as you can see that as indentation goes on, this rows of this or columns of this pillars that come in contact, and then contact area increases, and then the unloading starts, and then it again comes out of its contact and like that. So, by that process we can take advantage of both the mechanisms, and the force displacement plot, okay, looks like this. So, here as you can see that the hysteresis happens all through, because here, okay, this is a combination of both self adhesion hysteresis and the contact area splitting or like that, and as a result the hysteresis here can happen all through, and we can actually take advantage of this structures and like that. This channels does not necessarily have to be completely rectangular, they can also be V-shaped or can be this kind of inverted V-shaped and like that, and this has the advantage that we can make adhesive where the adhesion varies spatially. So it can be here as the distance increases the hysteresis effect decreases, but it will increases once again as it comes closer and something like that. So we can take advantage of this effect, so we can get some kind of spatially varying adhesion by having these channels oriented in a different mechanism, a different way. So these are adhesive with slanted microchannels, and the hysteresis that we obtain that can be scaled like this. The scaling relation we have developed in that particular paper by my student Dr. Arul is over here, and so if you are interested you can have a look at that. So we can have this comparison of hysteresis for these different cases. So for example, like this, for example, that for this channels with smooth wall is represented by two channels with smooth wall, with textured wall, with 3 channels with smooth wall and 3 channels textured wall, and with respect to delta means with respect to the depth of indentation, and you can see here that for this channels having textured wall has got much larger hysteresis, and then channel having this smooth wall like that. So 2 and 3 wall channels does not have much difference, because at the 3 walls the effect of the channel because the depth increases, so the effect does not increase much. So in fact 2 channels is good enough basically what it means, and as we increase the depth the contact area increases, therefore the hysteresis increases, and this hysteretic effect is more prominent for this 2 channels or 3 channels with patterned surface, textured surface. So that is the way we get over here. So we can have therefore both contact area splitting, we can have both this crack arrest initiation, and then we have this kind of like chemical treatment like self adhesion hysteresis. All these things can be combined to enhance adhesion without viscoelastic effect. In fact, we can also apply pressure inside this channel. So these channels can be connected to pressure pressure field, for example a pump or like that, and apply pressure. We can apply both positive pressure and the negative pressure and like that. And as it so happens that in the case of positive pressure there is a hysteresis actually increases, as is negative pressure this is actually increases further than the positive pressure and like that. So here this is the pressure which is presented here. So the data for this black one is without applying any pressure, there is atmospheric pressure open to atmosphere. Here it is negative pressure, it is positive pressure and like that. So we can get different hysteresis effect by applying the pressure also inside this channel, and these results can be found in detail in this particular paper of Dr. Arul. And here the data has been compiled for all these different cases for the channel, the skin thickness and all that. So if as you can see, if the thickness is large, you needed to apply more load and like that. So the hysteresis effect is actually even larger for the higher thickness and like this, and smaller thickness it is actually smaller and like that. But what is to be seen is that for each case positive side and also the negative pressure there is a minimal optimized pressure which is important to maintain. So both positive and negative pressure can be used for controlling or like tuning this self adhesion hysteresis. That is the message over here. Now I will go to describe another interesting effect. As I was telling you, it is about elastocapillary effect. So this elastocapillary effect can also be used for enhancing adhesion without this viscoelastic effect via this called crack arrest and initiation mechanism. So over here, so I showed you this film with embedded with microchannels. So those experiment and those channels that I showed you earlier were open to atmosphere. So that means the pressure inside was atmospheric pressure, 0 pressure basically, gas pressure is 0. But now what we do is we can insert some liquid inside it. Now what happens is that this surface of this particular material of this elastic adhesive, it has got affinity for certain liquids, and for the certain liquids it does not have affinity. So this, when you bring a liquid in contact with the surface of this material, its interfacial energy changes, and change in interfacial energy leads to different effect. So for example, if this interfacial energy decreases, so for example over here let us say you have put a liquid. As a result, this surface, okay, likes this liquid. So there is a weighting over here, means like this liquid is this surface is weightable by this liquid. Okay, then what happens is the interfacial energy will decrease, and if the interfacial energy decreases, then it has some excess surface energy available. That surface energy will lead to, or in other words we can say that because of the change in the interfacial tension over here, this curvature can increase. So as a result, there is a deformation that happens, this thin film that deforms over here like that. And on the other hand, if the interfacial tension decreases, then this particular surface deforms in a different way, because then the curvature needs to decrease. So when interfacial tension decreases because of the weighting of the solid surface by this liquid, okay, then the curvature has to increases, curvature increases. Okay, and when the reverse happens, when the interfacial tension increases because of the weighting, because this liquid and this solid, they don't like each other. So if the solid and liquid, they don't like each other, then I have shown you previously that the interfacial tension will increase. If they like each other, then the interfacial tension will decrease, like that. So curvature, when the interfacial tension decreases, curvature can increase. So what is the effect? The effect is something like this. When you have, let us say, ethanol, ethanol is weighted by this surface material called PDMS, polydimethyl siloxane. Okay, this is the diameter of this channel, 450 micron, and T0 is the thickness, skin thickness, and you put ethanol inside this channel, then ethanol can weight the surface of this material, and as a result, it is a highly weightable surface, weightable material actually. So as a result, the interfacial tension decreases. So the curvature of this here can of this channel, that can increase. The curvature can be increased, leads to this kind of bulging, okay, out of the surface of this elastic film, adhesive film, and it bulges out like that, and it goes up like that. On the other hand, if you have, let us say, water, and I will show you, or it is there in my newspaper and like that, that it will actually, where it is not weightable, okay, this bulging actually decreases, or bulging will opposite the side. So DMSO is also weightable, and here it is not that much weightable. So as a result, the bulging is there, but smaller quantity. Then we have got, let us say, perfluorooctane, even smaller by effect of bulging, because it is weightable, the interfacial tension decreases, but not that much, something like that. So this effect is called elastocapillary, because it is the capillary tension or capillary phenomena that gives rise to this deformation in the elastic film. So this effect is called the elastocapillary effect, and basically it is because of the change in the interfacial tension or surface tension of a solid that leads to this deformation. So here, for example, there is how does the cross section of the channel look like? So it is that picture. So here you see that the circular channel, this is the dash side that defines the circular channel which was there initially, and now you have put some liquid, and then you capture the side view, and when you put the liquid, there is a bulging that happens over here. Okay, so this bulging, okay, that kind of leads to some kind of arresting effect. I will show you that in a minute. What is the character of the bulging? It is irreversible. Okay, that has to be seen. So for example, I was telling water. So when you put water, then the bulging decreases, and then you remove water, and then you put nitromethane. Nitromethane is a weightable material, weightable liquid. So here the bulging goes up. So then you remove nitromethane and put water once again, the bulging will come down once again. So what it means is that this particular effect is completely reversible, and that is why it is basically a surface or interfacial effect. So here the bulging increases when that is weightable, bulging goes up when it is weightable surface material, and you remove the weightable material and you put this a non-weightable surface like liquid, that water. So PDMS is hydrophobic, so it does not like water, so the bulging decreases. Once again remove water, put nitromethane, once again bulging will increase. So this kind of phenomena that can go on over here, and here also, for example, in water this bulging decreases, and then you put ethanol, bulging will increase, and then ethanol also swells to some extent, this material, so it is not completely reversible for ethanol. Okay, so all these things you can see by this simple experiment. okay, all this phenomena that happens. Now this is the elastocapillary effect as I was telling you. Now how does the elastocapillary effect affects the crack propagation at the interface? So here this experiment is being done is the same way. So you try to lift this plate, okay, while putting some liquid inside. So this is a wettable liquid, so which creates this bulging up scenario, and then you go on playing lifting this plate continuously and see what happens. So this crack contact line that comes and gets arrested over at the vicinity of this channel and remains arrested for a long time, and then finally, okay, at some critical load, okay, the crack starts appearing from the other side and again propagates catastrophically and gets arrested once again. So what it means is that the surface of the adhesive is smooth, okay, no features, but we apply this elastocapillary effect that leads to this kind of bulging on the surface, and which is reversible of course, but this bulging effect or this elastocapillary effect that leads to this kind of crack arrest and initiation at the interface and leading to this enhancement in adhesion, because you need to apply load in order to overcome, okay, go over this channel crack arrest, so arrested to move this arrested crack. And so if you see the torque as a function of this lifting height, that is delta, you will see something like this, that for let us say when there is a smooth film, okay, with these channels inside or without the liquid with infill basically filled with air, let us say, so this effect will be something like this, okay. But when you put the liquid inside and then you do this experiment, the torque increases, okay, at the vicinity of the channel, and then it gets decreases drastically because the crack starts propagating once again. So the crack gets arrested here and then propagate. Once again the crack starts, energy starts building up, the force load starts building up, and at a critical load again the crack starts propagating. So crack arrest and crack propagation that continuously happens over here, and this elastocapillary effect leads to this enhancement in torque that is required, and you can calculate the fracture energy that is required to move this crack, and you can get that with respect to different film thickness and diameter of the channels, you can different amount of viscosity of all this kind of different data, different kind of adhesion strength you can get, and this is for the smooth film where there is no features, and this is for the case in a certain case number 7 is here, 750 micron is the thickness of the film and diameter of the channel is 710, which is filled with this liquid which is about 380 cp or something like that, and this liquid, okay, now leads to this enhancement, about 30 times enhancement of this adhesion over here. So by varying this channel diameter, skin thickness and all that, you can vary this fracture energy of the surface over a very large range, and that is what shown here, and you can actually rearrange these bars and you can show that from very small value to very large value. So you can do over the whole range by using this elastocapillary effect as we have presented here. In fact, we can also do some other things. You can also create a directional adhesion. For example, here there are channels are in pairs, not just one channel but pairs of channels, and this is one pair, this is another pair, and that, and the flexible contacting plate is brought in contact with the surface of this adhesive, and then you try to peel it or lift it from that plate, and let us say if they are filled with air, or let us say they both are filled with oil, or let us say one is filled with air and one is for oil. So this leads to quite interesting things. So for example, if it is air, then it is symmetric for both the cases, symmetry maintains. If it is completely total filled with oil, again it is symmetry maintains. But over here, if you peel it, if the crack fronts propagate from this direction, there is something that happens. If the crack front propagates in this direction, where there is only filled with air, okay, something else happens. So that is what we like to show you here, that for 1 and 2, okay, when they are oil filled or air filled, okay, then in that case this load remains here, something like this. So both the channels are equal, no asymmetry there. No, it is actually not the, it is all actually both the cases are oil filled. In one case, case 1 is oil filled, and the case 2 is that it is oil filled, okay. The first one is oil filled and the second one is air filled, okay. So in that case, case 1 and case 2, okay, in both the cases the load displacement comes very similar. So that means, so if the crack sees this oil at the first, then it doesn't have much effect. Then this case 1 and case 2, that means the crack first sees this oil filled channel, okay, then it is 1 and 2, the difference is not much there. But if it is sees the other, means like when you propagate from this side, so it fills first this air filled channel, then the oil filled channel, then this effect is enormous, and you can see the increase in the torque that is required to drive this particular crack at the surface. So basically it demonstrates this effect that one can not only create enhanced adhesion, but also create a direction dependent adhesion, okay, by employing these mechanisms which are non-viscoelastic. Here is the summary of this result over here, that if you have no channel, only smooth, so it is here, it is about 42 millijoule per meter square. But if you have this case 150 is both the channels are filled with, I think this is this case, okay, so both the cases are filled with channel, then of course this effect goes up enormously. But if it is otherwise, let us say that S1, the gap between the channels is S1 over here, and this green is when the crack propagates from this side. So the crack is always propagate from this side, this case, okay, in which case it sees the crack sees the oil filled channel first, that case, okay, and this other case, that means this is this case, green is this, and the other, yeah, green this, and then this case, they are same, they are case 1, these are almost same basically, that is what it shows. So and the case 3 is over here, okay, where in this case the opposite case, okay, where the crack is first sees the empty channel, then the filled channel, then it is quite high, and the gap between the channel also plays a role, and if it is of course both the channels are filled with, then the peeling torque, the fracture energy is very high. So like that, so one can actually manipulate with this geometry which want to fill these channels, okay, that helps. So basically what we have analysis, so we have done this films, adhesive films with pattern on the surface, also pattern at the bulk of these adhesives and bulk of the adhesives and like that, okay, and then we have filled with oil and we filled with air and all these things. Now how do we analyze these results or look at it, what we know what exactly is happening and how that is happens. So one thing can be thought of is that having this kind of channels or having this kind of patterns, or let us say these patterns and like that, in addition to this self adhesion hysteresis, other phenomena, that also alters the spatial modulus of this film. So the modulus of this elastic film that now varies spatially, okay, and then in some cases, in which case there are patterns, it also leads to, let us say, surface thickness variation. So adhesive layer can have both thickness variation and the modulus variation. So we can look at this the results that we presented, okay, on this light, that we have got an adhesive in which case we have got the thickness varies spatially and the modulus also varies spatially. So we can look at like that, and we can think of these experiments in this kind of adhesive, okay, which has got this modulus and thickness variation. So let us see that how you can analyze these adhesives with spatially varying modulus. So if we try to do that, okay, we will have to write the stress equilibrium relations, and it seems that stress equilibrium relation goes like this. So in his case, since the modulus is not constant, it is a function of x, so this additional term that appears. So I am not going to analyze, solve this problem, because we cannot solve this problem analytically, but I am just going to develop these equations, and then I can tell you that this can be solved by using numerical methods and all that, okay, that can be done. So here this is the stress equilibrium relation, one relation, the second relation is over here, and as you can see in both the cases, this modulus effect that comes. So this is the incompressibility relation that is there. So now we can, so this here we are discussing only spatially varying modulus, that kind of case, and then we can apply this dimension analysis, and this is that lubrication approximations all we can use, and by that we can simplify those stress equilibrium relations to this form. So here mu 0, so the mu is equal to mu 0 into function of x, that is what we have written. So function of x has got this form, 1 plus delta sin kx. So I have just considered the sinusoidal variation, you can think of some other variation as well, but this is periodic, let us say. So from that consideration I have thought about this function as varying like this, and then you can those simplified equation we can do the integration over the z and then we can use the incompressibility relation and then obtain U and then W and like that. So, all these things we have done earlier, very similar way we can do over here, and then we can use the boundary conditions that we have used earlier, and we can get this equation. So, this equation remains valid for x less than 0, and then here this quantity zeta over here, which is given by this equation. If when you solve this, we will get something like this equation. Now, this equation 6th order equation, and here is 4th order equation, and this particular additional term that comes because of the modulus variation. So, these equations can be solved by using this integration this boundary conditions, okay, that is there. So, this we have described all that, and here what we have used is that for the cat propagation at x is equal to 0, okay, at the contact line, that there is a critical stress that is reached sigma c. So, this critical stress can be defined or like that in this theory that is done. This particular paper of mine, you can have a look at it, and when you have this mu varying as sinusoidally like that, okay, we can get this f as a function of a, means as the peeling front propagates, so the a increases, and we can see how the load behaves, and the load goes this kind of periodic behavior. So, this looks very similar to the experiments with this channel embedded adhesive that we did. So, I will stop here today, but this analysis can be taken forward further, and I will briefly present some initial equations that we developed in regard to when this film has both spatially varying modulus and spatially varying thickness in my next lecture. Thank you.